Hello everyone, my name is Jesper Gaarsdal from Aalborg University and SynergyXR, and in this video I will present our research on AssemblyNet, a point cloud dataset and benchmark for predicting part directions in an exploded layout. Exploded layouts are visual representations that display the components of an object slightly separated by distance, usually used to illustrate the assembly of mechanical objects. When broken down, an exploded layout is created by assigning each part a direction, a distance, and an order in the sequence in case of an animation. They are crucial in technical documentation, assembly instructions, and educational materials, as they clearly show the relationship and assembly sequence of various parts. This makes them essential tools in manufacturing and repair, helping technicians and engineers understand the inner workings of machinery and equipment. In this work, we focus on determining disassembly directions of parts using point cloud-based deep learning. Traditionally, exploded views are created manually, which is a time-consuming process that requires expert knowledge about the product or object that is disassembled. Previous works have explored different algorithmic approaches to automatically generate disassembly sequences and exploded layouts, but these methods often compromise in accuracy or require significant computational resources. In recent years, deep learning is being used to solve a vast array of complex tasks with great success, yet no previous studies have explored its use for creating exploded layouts. In this work, we introduce AssemblyNet, a novel point cloud dataset for predicting part directions in exploded layouts. We provide annotations for both regression and classification tasks, and we report benchmarks for commonly used point cloud-based networks, as well as a novel two-path network architecture. With this approach, we aim to make the automatic generation of exploded layouts more efficient while maintaining the accuracy of previous methods. The dataset was created by sampling point cloud from 3D models of real-world industrial assemblies and Lego models. The dataset is made from 44 assemblies divided into 495 sub-assemblies by manually disassembling the parts. By using each part from each sub-assembly, we end with a total of 5,420 samples. Each sample consists of two point clouds, the part and its sub-assembly. The points are sampled by randomly selecting triangles from the mesh of parts, and the final part and subassembly point clouds are normalized relative to each other to preserve the spatial information of where the part is positioned in the subassembly. The ground truth labels were created manually. For the regression task, the labels consist of normalized 3D world space directions that parts should be disassembled in. For classifications, the number of possible world space directions are discretized into 26 classes, representing directions at roughly 45-degree angles to each other. A sample is then assigned the class closest to its actual direction. The dataset contains both 512-point and 1024-point point clouds, providing a means of prioritizing either computational resources or accuracy. The dataset is divided into training, validation, and test sets, following the traditional 80-10-10 split. To avoid data leakage and contamination, each assembly is represented across all splits, but each subassembly is only represented in a single split. The dataset is heavily imbalanced towards the cardinal directions, which does reflect real-life scenarios where most part movements align with the global axes. Our proposed network architecture employs a two-path approach, processing part and subassembly point clouds separately to capture distinct features. The main path processes the part point cloud to capture specific geometric features of the part. The purpose of the subassembly path is to add context regarding the spatial relationship between the part and the rest of the subassembly, using cross-attention between part and subassembly features. Inspired by recent advances, the architecture uses matching encoder and decoder layers. For the encoder layers, we test using two different methods, the edge-conf layers from the DGCNN network and the point set abstraction layers from the PointNet++ network. While rotation augmentation has been found to generally decrease performance and is usually applied to achieve rotation invariance, we use it here for the opposite effect. As our ground truth is a world space direction, predictions should change with the orientation of the point clouds. We perform the rotation with a 30% probability and select a random new class that we rotate both point clouds and labels to. For our classification results, we report the macro accuracy of the tested models. In general, the PointNet++ based networks outperform all other models in the original distribution of classes. For the equalized distribution, where each sample is rotated to each of the 26 classes, the two-path networks show better performance than their base models, indicating that the two-path approach generalizes better to different orientations. For our regression results, we report the angular similarity between the predicted directions and the ground truth, as well as the macro accuracy when discretizing the predicted directions to the classification labels. For the angular similarity, the base models perform slightly better than the two-path variants. When converting to macro accuracy, performance drops significantly for all models. However, as with the classification results, the two-path networks appear to generalize better than the base models by outperforming them on the equalized distribution. In order to determine the nature of the errors made by the best performing classification models, we measure the angular similarity between the predicted classes and the ground truth. By doing this, we find that most errors result in either opposite or orthogonal directions. While we haven't examined this further, we believe this could be attributed to the loss of detail when representing the 3D models as point clouds, as parts may appear symmetric and connections to neighboring parts may be lost. It also appears like the models may fail to learn the spatial relationships between some parts and subassemblies. To determine the effect of applying rotation augmentation, we performed an ablation study for the classification models on the validation set, evaluating with and without rotation augmentation across both original distribution and the equalized. We find that while rotation augmentation does decrease performance on the original distribution as expected, it significantly improves performance on the equalized distribution for all models. In conclusion, we present a novel machine learning-based approach for determining part directions in automatically generated exploded layouts. To achieve this, we have presented the public AssemblyNet dataset, consisting of point cloud pairs of parts and subassemblies, annotated for both regression and classification tasks. We have also proposed a two-path network architecture, and we have reported benchmarks of 2 variants of the two-path network, as well as 4 other well-known point cloud networks. This study marks an important step in the automatic generation of disassembly sequences and exploded layouts, as the first study to apply machine learning methods to this task. In future work, we would expand the AssemblyNet dataset to include not only more samples, but also include assemblies from other domains, such as furniture. We would also expand the benchmarks by testing other and more recent network architectures. And lastly, it would be interesting to test other representations of 3D models besides point clouds. Thank you for watching.